So we're continuing in chapter or section 22.2. The next reaction that we're going to look at is called the HVZ, or Szalinski reaction. So Volhard, and Szalinski are the three people that worked on this reaction. This reaction only works for carboxylic acids. And to my knowledge, it only works with bromine, Br2. Also needs some PBr3 and water as a step 2. And this puts a bromine in the alpha position of a carboxylic acid. So conditions, we only can do this with carboxylic acids. We cannot do this with any other type of carbonyl compound. Like, we can't do this with ketones or with aldehydes. And we can only brominate. We can't use any of the other halogens, which is probably not a big deal because the halogens are all pretty interchangeable. The mechanism for this reaction is really not understood, at least not at the time of the printing of your textbook and not at the time of my own personal education. But here is a sketch of, and this is definitely not going to be a mechanism, a sketch of what is believed to happen, a sequence of steps. So the PBr3 starts by converting the carboxylic acid to an acid halide. This is an acid bromide. In chapter 21, we did a lot of stuff with acid chloride, so this is kind of like an analog of an acid chloride. And the acid chloride will tautomerize itself to make an enol, halogenated enol. The halogenated enol reacts with the bromine, and in this reaction, it's not a normal addition of bromine across the double bond because it's not a normal double bond. We just get one bromine put on there, and then in step 2, when we bring the water in, we hydrolyze the acid bromide back to a carboxylic acid. And the hydrolysis of the acid chloride was a reaction that you looked at in chapter 21. So at least this very last step is not totally bizarre. But the rest of the mechanism, or pseudo-mechanism, it is kind of a weird reaction. The next reaction that we're going to look at in this section is base catalyzed halogenation. And in this reaction, there's actually two different ways that we can do, or two different types of reagents that we can use for the base catalyzed reaction. So in one version, the first version that we're going to look at for this reaction, the alkyl groups that are on the ketone are not methyls. I'm drawing 2 ethyls, but we're going to make a note of this. Specifically, they're not methyls. I'm going to use bromine. This is base catalyzed, and we usually just use hydroxide for this. And we end up just doing a simple putting the halogen onto the alpha position. So this could be, let's make a note of this, we could be doing this with Cl2. We could be doing this with I2, so any one of them will work just fine. This is not a step 1, step 2 reaction. These things are mixed together simultaneously. These, whatever the R groups are on this ketone, or if it was an aldehyde, they can be pretty much anything as long as they are not methyls. And also they do need to have an alpha hydrogen somewhere so that we can do the substitution. On paper, this is exactly how the reaction goes. In the real world, this reaction is very favorable. So in reality, it's just going to alpha halogenate the bejesus out of itself, and you're going to end up with halogens just totally saturating the alpha sites. So this is what you would get if you were doing it in the lab. But on paper, this is the right answer to a question that was asking you about base halogenation. And this is not the first time that we've had this sort of situation. Friedel-Crafts was another one where in reality the reaction would occur over and over and over again, but on paper we would pretend like the reaction would only happen one time, and that mono reaction would be the correct answer to any sort of question that you might be asked. Let's look at the mechanism for this reaction, because it is quite nice. Because it is a base catalyzed reaction, and the base catalyzed mechanisms are always very pleasant. So in this reaction, the base, first thing that it does is go after one of the alpha hydrogens, and we're going to put that lone pair of electrons onto the alpha carbon. So we end up with lone pair and a full negative charge on the alpha carbon, which then goes out and attacks the halogen. So it's nice and simple. Now, this the condition that this is not being done on an aldehyde or a ketone that has methyl groups, that is not because the methyls prevent a reaction from taking place. That is because if you have a methyl out there, it's going to do a different reaction, which we call the haloform reaction, which you may have done in lab, because it is a very common test that we do if we're trying to do like testing unknowns. You're trying to identify your unknowns. The haloform reaction is a test to determine if we have a methyl ketone. So it can only be done if we have a methyl out here. At least one methyl. The haloform reaction is a two-step reaction. Starts out the same, Br2 with OH minus, but then we're going to need a step 2 where we bring in some acid, H3O plus. And this actually converts the methyl part of the ketone to a carboxylic acid. So it kind of looks like it's not even an alpha reaction in general, because we are literally just totally chopping off one of the alpha carbons and all of its hydrogen. But this reaction does occur via alpha halogenation. So we're going to take a look. Again, this is not going to be a mechanism, but just kind of a schematic of how this reaction probably occurs. And I'm going to use the same ketone, but I am going to turn it around so the methyl is on the right hand side. And so when this reaction starts, the first thing that happens, which is our step 1 with the Br2 and the OH minus, this first step just totally saturates that methyl group with bromines. Just like we talked about up above. So it just gets completely filled up with bromines. And the hydroxide ion comes in and attacks the carbonyl carbon. I'm not trying to make this look like a mechanism, because this is a reaction. The mechanism is not really established yet. So we get this thing. I'm going to write this as CBr3. Instead of writing all those bromines out. And we've added an OH group on there as well, because we did attack the carbonyl carbon with an OH group. The O minus comes down to create a carbon-oxygen double bond, and it spits off this CBr3 as a leaving group. So we have now a carboxylic acid, and we have this CBr3 minus. My carbon looks like an oxygen there. It's a C. C minus, which is a really, really, really strong acid, or excuse me, a really strong base. So it's going to go after this carboxylic acid that we formed, and we're going to end up making deprotonated carboxylic acid and HCBr3. This deprotonated carboxylic acid, we've got that step 2 H3O plus that we're bringing in, so it's going to put the proton right back on it, no big deal. And this molecule that is produced, that our leaving group that's been protonated, this is a Haloform. That's its generic name. For this particular one is bromoform because it's made with bromines. So you could take a guess what chloroform would look like now that you know that.